L1 truck-on-truck head-on. In this next case, we will look at a truck-to-truck head-on scenario. The test vehicles, in this case, are Land Rovers. In this scenario, Wabtec conducted the work via an independent verification facility during its lab-scale trials. Wabtec viewed this as an important validation step before proceeding to site trials. In this case, we connected the PDS system to the University of Pretoria kit to accurately analyze when we get a signal and at what distance for L7, L8 and L9 commands. Let's talk about what we just saw. These trucks are on a linear path. One vehicle is stationary and on the left. The vehicle from right comes in from a far distance, 50 km an hour, on a collision path with the other vehicle. As you can see, the vehicle will automatically slow down and stop with a 10-meter stop gap under L9 intervention controls. As you will note, the vehicle automatically moves from L7 to L8 to L9 slowdown, then eventually to a complete stop command under the PDS system. This is enabled through Wabtec's collision awareness system and vehicle braking system. What was just shown is one of the most dangerous high-risk scenarios due to the high speeds involved. In this scenario, we will look at an L5 truck passing case. As you can see, two ADTs are on a straight linear path. One truck is stationary and the other at 15 km an hour. The ADT moving at 15 km an hour would not receive a slowdown or a stop command because the ADT is passing the truck at a gap above 5 meters, which is within a safe distance zone. Also, the gap between two cones is set at 5 meters. The two vehicles stay at 5 meters apart, and therefore no intervention is required. This is an important scenario, as you don't want unnecessary stops. For instance, if the vehicle had to make multiple unneeded stops while driving on a haul road, this would have a massive impact on productivity of the mine site. Bottom line is that you need to make sure you can pass safely, within a safe distance, so as not to impede productivity of the mine site. In this next case, we will be looking at a loss of control or truck speed limiting by geofence scenario. The cones highlight the start of the geofence. As you can see, the vehicle gets up to speed at 30 km an hour as it approaches the cones. As the vehicle gets close to the geofence, the vehicle needs to slow down to 15 km an hour. Important to note, the vehicle is governed to 15 km an hour between the two cones. The operator will most likely have their foot flat on the accelerator. The vehicle would not be allowed to exceed 15 km an hour. As soon as the vehicle exits the geofence, the vehicle is allowed to return back to 30 km an hour. This is a good example of speed governing within a geofence. In workshop areas, we want to ensure that the speed of vehicles do not exceed a certain limit. By applying geofencing across the entire mine site, operators are limited to the speed of the designated geofence area. Also, you can have a geofence within a geofence. For example, you could have a mine-wide geofence of 40 km an hour, and inside a workshop area, you could have a geofence of 5 km per hour. The vehicle will adhere to the geofence with the most stringent condition.